Good morning.
Oh shit, I'm wearing a hat.
Good morning.
Good morning.
Good morning. Good morning. Good morning. Oh, nice hat. All right, I need to step up my hat game. Good morning.
Good morning.
All right, go ahead, either privately or to everyone, respond to bell work.
What's the difference between weather and climate? Motherfucker, I don't know.
Yep. Good morning.
Good morning.
Ibuprofen in my body. I need surgery.
Good morning. How's everyone doing?
Good.
Well, I stepped up my hat game. This is a handmade hat.
I have half a hat.
You do have half a hat. I hear something in the background. All right, make sure you respond to the bell work in the chat. We're going to get started in just a few seconds here. I'm liking all these responses. And by the way, this is a picture of Cuyahoga Valley National Park. Oh, nice hat, Mr. Tout.
I try.
All right, there we go. Okay, so the difference between weather and climate, and it's great to see everybody. We're going to touch base today about the expectations for spring break and what people said in the survey. And we're also going to do lecture 7.2. So lecture 7.2 is all about the climate. And that's why I asked the question this morning about weather and climate. So lots of really good responses. I'm seeing stuff like weather is a daily thing, climate is the average weather pattern over many years. The difference is the time scale they're measured on. Weather is a normal pattern and climate is a change over the years. All excellent answers. So that summarizes it really well. Whoops, I went one step forward. So again, we're going to be doing lecture 7.2 today. And we do have a little over 30 days until the external assessment. I wanted to go over the spring break schedule. So I will make myself available, and I can't speak on Mr. Tout's behalf, but I'm sure he will be making himself available as well for at least a little bit of time.
I disagree.
You disagree?
No,
Right
that's,
under the bus.
yes.
All
No,
right,
no, Mr. Dutton is correct. Listen to Mr. Dutton.
Okay. So Monday, Wednesday, and Friday, I will be available on Zoom from 9 a.m. to noon. There won't be any like structured classes, but what I will be doing is Q&A. So if you have questions about coursework, if you have questions about current events, I'll be cycling through some meditation and exercise breaks. So in case you're looking for any sort of like, good meditative techniques, Mr. Tout's really good at that stuff. And if you're looking for any sort of opportunities for exercise, we'll be doing some of that as well. And I'm hoping to recruit some folks to help me do that. And then we'll also be doing some goal setting, some routines, setting routines so that we have like kind of, some long-term plans so that you're not just sitting there and, putting in an hour of work a day and having that be it. And I just wanted to review really quickly as we enter on the weekend. and there's less structure over the weekend, and maybe you're out of your normal weekend routines, making sure that you're doing some of these things that we talked about before, the reading, the relaxing, the non-screen time, starting a new hobby. You've got the time to really develop a new skill. Reaching out to others. Yeah, we've got 13 people on this right now, and we've had up to 20 over the course of this week. But I think, a lot of people are seeing the value in these classes. Some people are taking the time to do these later on YouTube. But you never know who you might connect with if you reach out to people who might be sitting there and going, you know what, I'm just gonna like watch movies all day, this, that, and the other thing. And they might be feeling, a little lonely. So try to connect with some folks, especially the folks who are in your class, who you haven't seen, you haven't heard from. Like I said, try to keep up with your studies as much as you can. Review previous topics in order to prepare for the EA. We'll be doing a big review as well, but you should be doing that on your own. And we'll be working on this during spring break, but try to make a schedule for yourself. Try to settle into those good routines. It's okay if you don't stick to your schedule 100%. Wow, that's an interesting schedule I got there. So let's dig into lecture 7.2. Before we do that, Mr. Tout, did you have anything you wanted to go over?
No, not right now. Yeah.
Okay. So let me find the right one here. There it is. The Nearpod is VDCWH. And like we did last time, feel free to respond either by unmuting yourself or by responding in the chat. The more you participate, the better an idea I have of what you understand and don't understand, so it really helps. All right, who needs more time to get on the Nearpod? Raise your hand or something. All right, I'm going to assume everyone's good to go.
Oh.
Oh. All right. So as you said, the difference between climate and weather, we're talking about short-term versus long-term. So weather is short-term, temporary conditions. For example, I've got my window open today because it's 60-something degrees, which is awesome. I love having my windows open because it really, gets the fresh air going. But tomorrow, it's supposed to be nice and chilly. It's supposed to be back to the 30s. That's because, weather can be temporarily warm, temporarily cold, but it's still really early springtime. And we expect that the climate is going to be overall maybe like in the 40s, and it's going to be rainy. And so climate is that overall average weather at a place over a period of time. Now we are seeing the climate change, of course. We're seeing climate shift. We're seeing winter start later and spring start later. So typically it gets and stays warm, further into spring than it has in the past. So we are seeing climate actually changing over time. This next one is a video, and I am going to, let's see, who wants to play it on your own? Might be better to play it on your own rather than relying on my stream. All right, so I'm not hearing or seeing opinions. I'm going to choose the option where you guys can play it on your own. So go ahead, start that video. And make sure you have yourself muted so that you're not broadcasting the audio of the video.
Mm.
All right, let me know if you're not done with the video yet. Okay, so let's chime in with a couple things about the video. So what regions of the Earth receive more energy than other parts? You can respond on the chat or unmute yourself.
The tropics, the equator of the Earth get the most sunlight, and the poles get the least.
Awesome. So the most energy is received in the tropics. Excellent. And what happens in the subtropics? That would be 30 degrees north and 30 degrees south. What kind of air is received in the subtropics? So let me ask that in a different way. That air from the subtropics is descending air that moved north or south from the equator and has already dropped its water, so it's already precipitated, but it's coming from the equator, so it's warm. So then that warm, dry air drops on the subtropics. So what would you find in those areas of Earth, 30 degrees north and 30 degrees south latitude, where that warm, dry air is constantly hitting the surface of the Earth? So places that you might find 30 degrees north and 30 degrees south would be like Arizona, southern Arizona in particular, the middle of Australia. There's a very famous large area in the middle of northern Africa that is 30 degrees. That receives lots of very warm, dry air. What all these places have in common? What kind of biome is that? Hot and dry. Yay! They are all deserts. Thank you, Nadia. So we tend to find deserts there because that air has already released all of its moisture, but it's still warm. And so it's not delivering rain. And that's why deserts tend to be hot and dry. All right. There was something else that was mentioned that in part of this circulation, the oceanic and the atmospheric circulation, in our part of the world, so in between the subtropics and the polar regions, we tend to get all of our weather from what direction? What direction do we look to for all of our weather, the west or the east?
The east?
Nope.
Ooh. Go west.
Yep. So we tend to see all of that weather come in from the west. So if you're ever wondering what the weather is going to be like tomorrow or the next day, check the weather for like Colorado, California. There's some clues there as to what the weather might be in a couple days. Obviously, the weather is more complex than that, but generally, the winds are coming out of the west, and so they blow whatever weather is in the west to us over the course of the next day or two. Make sure that when you are watching a video, you're taking some notes. I took some notes, but those are important things to take notes on. Also, she mentioned how the ocean is denser than the atmosphere, and that it has what's called a high heat capacity. I wanted to really make a note of that, and what that means is that the ocean is capable of storing lots and lots and lots of heat. It's also capable of releasing lots and lots and lots of heat. So what that means is that as our atmosphere warms up, a lot of that heat is being stored in the ocean. And so we are not seeing the worst effects of the temperature rise because a lot of that heat is being stored in the ocean. But it also means that over time, that heat that is stored in the ocean is going to be released back into the atmosphere. And so there's this time delay between when we actually do these actions affecting the climate and when we see their effects. So the atmosphere, as we've been talking about, plays an enormous role in climate change. And one of those pieces, of course, is greenhouse gases. You all did a brief presentation on greenhouse gases, so you're familiar with some of those. But the beginning of this whole greenhouse gas process and how it is that heat is retained is that energy needs to come in from the sun. Energy from the sun is along the electromagnetic spectrum, right? And there are all sorts of different waves that are coming from the sun. There are really long radio waves that come in. Those radio waves pass right through our atmosphere and are able to impact the Earth directly. We don't get impacted by those radio waves. It's not like you can, tune your radio to listen to them. But those radio waves are impacting us all the time. They're just not doing so in any way that we feel. Infrared radiation, we actually detect as heat. Infrared is a nice long wavelength, and we feel it as heat. And believe it or not, only a fraction of the infrared radiation coming from the sun do we actually feel on the surface of the Earth. Our atmosphere captures a lot of that infrared radiation, a lot of that direct heat, and protects it from hitting the surface of the Earth. Visible light passes right through our atmosphere, and we're able to see that visible light. UV radiation, we know that there is a layer that is protecting us from most of that UV radiation. What is that layer called?
Ozone.
Hey, ozone layer, excellent. And then our atmosphere is really good at blocking out things called X-rays and gamma rays. And that's a good thing. You know that X-rays are not good for human health, and gamma rays are particularly not good for human health. These are very short wave. This is very short wave radiation. X-rays and gamma rays are very short waves, as denoted by how spinny these waves are. And that gets blocked out by our atmosphere, which is a good thing. So we end up with mostly visible light, some radio waves, a little bit of UV, and a little bit of infrared. Now that we have that information, we can understand that generally what we have coming in from the sun is shortwave radiation. In other words, visible light and UV. All right, so that shortwave radiation is visible light and UV. And on land, where it's darker, a lot of that shortwave radiation is absorbed by the surface of the Earth. And what happens is, as it's absorbed, some long wave radiation, all right, it changes in frequency, is emitted, all right? And that is infrared spectrum. Remember, infrared is kind of the same thing as saying heat, all right? So long wave radiation is emitted when shortwave radiation hits the surface of the Earth. And so that gets emitted as heat. A little bit when the surface of the Earth is impacted on land, a little bit is reflected as shortwave radiation, meaning a little bit is reflected as light. So we have a lot of light coming in. Some light gets absorbed. Some light gets reflected as heat. Some light gets reflected as just light, and that's why we can see it. Now, when that same sunlight hits something like snow or ice, there's very little that is actually absorbed. Most of it is reflected as light, and that's why it's so bright. Some of it, but less, some of it is reflected as infrared or as heat. So there's a difference between what happens on land and what happens on the ice or snow. And there's a difference in what gets reflected. On land, there's a lot more heat that gets radiated back out and less light. On snow or ice, there's a lot more light and less heat. There's also a difference in how much gets absorbed. You see this circle is bigger because there's more shortwave radiation that is absorbed. And so that means that darker places on Earth, like land, they end up heating up faster than lighter places like ice or snow, and they absorb less heat. Questions about this slide? There's a lot going on here. All right. So greenhouse gases factor into this whole equation because greenhouse gases like to trap that heat. And they also like to trap some of that shortwave radiation, some of that light. All right, some of the infrared radiation does pass through the atmosphere, but some is absorbed and re-emitted to the surface of the Earth by greenhouse gas molecules. So that infrared radiation that normally would be able to escape out of our atmosphere and back into space is actually bounced back to the surface of the Earth by these greenhouse gases. So these greenhouse gases act as a blanket, keeping that heat in instead of allowing it to escape. So greenhouse gases do not make heat. Greenhouse gases just trap heat. And the key here is that you may be asking yourself a question, which is, well, if greenhouse gases are able to trap heat, why are they not just stopping it when it comes from the sun? But remember, that shortwave radiation is able to pass through those greenhouse gases. That light energy is able to pass through, all right? But then when it bounces off of Earth, it turns into longer wave radiation that can't get past those greenhouse gases. So greenhouse gases are really efficient at letting in light, but trapping heat. So take just 2 minutes and make a quick drawing showing this difference between the light, the short wave, on open ocean versus ice, and showing what happens as far as the reflection of heat and visible light. So we should see light coming in to both the ocean and the ice, and then I want to see what gets reflected back. And over my right shoulder is the timer. We got a minute. All right, time is up. Make sure that you've submitted your drawing. I'm seeing some good drawings. Make sure they get submitted. So here we have a really excellent drawing by Mr. Tout showing that as solar energy, as that light hits the ocean, hits the water, that some of it gets re-radiated, but way more gets re-radiated when it hits the snow or ice. All right, we're gonna move on. I'll take a look at the drawings later. So, as we always do, we need to consider the impact of humans on this whole thing. Well, we know that we increase greenhouse gas levels in the atmosphere, and there are some impacts of that. One of the impacts is that there's an increase in mean global temperature, meaning the average temperature over the whole Earth. There's an increased frequency and intensity of extreme weather events, for example, this tornado. There's the potential for long-term changes in climate and weather patterns. So what we see here is carbon dioxide levels over time, over the last 400,000 years, bouncing up and down between 180 and 300 parts per million. And we see that we are currently well above this. In fact, we're at like 415 parts per million, so somewhere up here. And so this graph is just going up and up and up. And there's also a rise in sea level. All of these states are susceptible to rises in sea level as sea level increases. Notice that we are not at risk of being impacted by sea level rise. However, if a lot of people from these areas lose their homes and have to move inland, then guess where they're going to move? So there are potential impacts of climate change. Some of these actually we're seeing already, but there are areas of the world that currently already have water availability issues, and that will just increase over time. So all of these places that are in the orange are places in the world that already have water availability issues. And these also correspond with where we find deserts, especially in the United States. This would be 30 degrees north, and here we would see 30 degrees south. A lot of these places already have issues with water availability, and again, that will only increase. And here we have distribution of crops was going to change. And excuse me, what we see is that in some places where it's green, they will be able to grow more crops as the temperature on Earth warms up. But all the places in yellow or orange will be less and less suitable for growing crops. And we see that's particularly an issue in Europe less suitability, and also in the southern United States. Other impacts of climate change: lower biodiversity. We knew this is going to be a problem already with the deforestation in the rainforest. And also what is called coastal inundation. So along the coast, seeing there being rising sea levels, and with any sort of hurricane or storm, tropical storm going on, every time that tropical storm happens, that storm surge, that increase in sea level that's temporary, will cause more and more damage on land rather. So we see more and more inundation happening as storms increase, as sea level rises. Other impacts include ocean acidification. So as carbon dioxide enters the ocean, it combines with water to form carbonic acid. And what that means is that there's less carbonate ions for these corals, mollusks, and other marine animals to make shells with. And that ocean acidification means there's less marine animals. And it also makes the water more toxic for other organisms that live in the ocean other than those things that make shells. Damage to human health. We see there's a wide variety of different things that can happen as a result of climate change, both physical health, mental health, and the health of entire communities. These are very real impacts: increased aggression, increased violence and crime, increased social instability. So the more that we can do about it now, the less those impacts will have on us as a society. So really quickly, add one post here. What do you think is the most critical impact of climate change? Choose one of them and make your post. Teacher. My name is Teacher. I don't even get a name.
Nah, man, Mr. Dutton, your name is Bread Man, bro.
I'm the bread man.
You
Yeah.
have no name.
Man, teachers need validation too.
Right. Good, good, good. So loss of biodiversity, sea levels rising, ocean acidification. All right, I'm gonna move on from this. Let's get to the quiz. I mean, not yet, but I wanna get to the quiz. Yes, I do look like Chef Boyardee. All right. We've talked about greenhouse gases, we've talked about the impacts of climate change, and we've talked about feedback mechanisms. This subtopic is bringing all of these different concepts together. So I just want to remind you of what positive and negative feedback is. So positive feedback is that the thing that happens, for example, melting of ice, warms up the ocean, which means that more light is absorbed by the ocean, which means that more ice melts, which means that more light is absorbed, which means that more ice melts, which means more ice, blah, 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 blah. Positive feedbacks. Positive feedbacks are not good, generally, right? Don't get distracted by that positive word. Positive just means that the effects create more of the causes, which creates more of the effects, which creates more of the causes. In negative feedback, what happens is that it works against making the cause happen again. So for example, reducing carbon dioxide reduces the total amount of heat in the atmosphere, which means that people need to use less carbon dioxide in order to run their air conditioning, which means less carbon dioxide in the atmosphere, all right? Which means that there's less warming and fewer people need to run their air conditioning 24/7, all right? So negative feedback reduces the problem in the first place. Another way of thinking about negative feedback is that if your body is warm, you sweat, that cools down your body and you solve the problem. If your body is cool, then you put on more clothing, you warm up your body or you shiver and you solve the problem and you no longer have to continue doing the thing. Negative feedback is like breaking the loop, all right? So absolutely.
Can I give a real life situation?
Yep.
So if we give, if Adrian wears a crazy hat to an online session and we all give him positive feedback, what happens?
Continues to wear hats,
Yes, and guess what everyone else is doing?
wearing hats.
So we have a new status quo. We've made a change that's creating more and more change. In this situation, it's been amazing, but in terms of nature, do we want the status quo to change?
No.
We want the temperature of the planet to change. So no, in this case,
Well, I
positive.
mean, we want it to go down from this point, but like, yeah, we don't want it to speed up or warm.
Okay, awesome. Thank you, Mr. Dutton.
No, thank you. And so these feedback mechanisms come with a time lag. So in the case of wearing hats, yesterday, the hat game stepped up. And that caused today, everyone to come with hats. And we noticed that, you know, maybe some people, this is your first time on the class, or you weren't here yesterday and you're like, why is everyone wearing a hat? Well, with any sort of feedback, there is a time lag. There's a time lag between the cause and the effect. It just so happens that with our atmosphere, that time lag can be super long. Super long for humans, not long for the Earth. So what we see here is this graph is telling us exactly how bad that time lag is. The blue line represents carbon dioxide levels over the last 800,000 years, and the red line represents temperature. We notice that the carbon dioxide levels, they go up and down first, and then the temperature follows. Now, it's not as easy to see in some of these parts of the graph, but it is really easy to see right here that carbon dioxide levels have gone up and up and up and up, and temperature is lagging slightly behind, meaning this carbon dioxide that we've already put in the atmosphere, that is a baked-in effect. We can't do anything about that. We can stop emitting carbon dioxide right now, and temperatures are still going to go up because of this time lag. Now, if we stopped putting carbon dioxide in the atmosphere right now, that would mean that temperature would go up, but it would stop going up. All right, it would go up to some level, like 2-3 degrees Celsius of warming, maybe 4, but it wouldn't go past that. So we would be able to do something about the effects of climate change. But if we continue pumping carbon dioxide in the atmosphere, that temperature will continue to go up even as we're trying to solve the worst effects of climate change. So that time lag is really difficult for humans because we don't see the effects of our actions immediately. And another impact of how do we do something about climate change is different people have different environmental value systems. We know that technocentric folks see that technology is going to solve all of our problems. Now, it's true that technology can solve a lot of problems, but it's also true that technology can't solve all of them. Folks who have an anthropocentric worldview, people-centered, believe that people are the managers of the earth. And so it's true that we can manage the earth to a certain extent, but we can't manage everything on the earth. It's too big and it's too complicated. Ecocentric folks, or nature-centered, think that we need to do minimum disturbances to nature. And again, that works to a certain extent, but you can't control everyone's actions. And so there is something for everyone here. And the ideal solution is a mix of these different approaches. And unless we kind of come together around how we're going to tackle climate change, if people just stay in their own lanes and they say, here's the solution and there's no other solution, or here's the solution and there's no other solution, we won't actually come to a solution that will work for everybody. There are, excuse me, there are lots of different global climate models that help us understand how the climate is changing. Some of them are very complex. You may be looking at these graphs going, what the heck? There's a lot of numbers on here. Every one of these lines represents a different model and a different projection over time. If we just look at the observations of the temperature and carbon dioxide levels on Earth, that's called the simple model. And that simple model, it doesn't actually reflect the warming that we are actually seeing on Earth. We are seeing more in this red area than the green area, all right? So we have to use complex models in order to actually model what's going on with the Earth. That's what I want you to take away from that. The AOGCM is the Atmosphere, Ocean, Global Climate Model. And we saw that at the beginning with the video, that we have to take into consideration not only what's happening with the atmosphere, but what's happening with the ocean and how those things interact with sea ice and the land in order to take into account all the different effects of climate change. All right, so when AOGCM is mentioned, it means that it's taking everything into account, not just how many greenhouse gases there are, but how that impacts the ocean and how that impacts the atmosphere. There is what's called a degree of uncertainty. Go ahead.
What were the letters? O, what?
AOGCM.
Okay.
Atmosphere, Ocean, Global Climate Model.
I put it in the chat.
Oh, awesome. There is a degree of uncertainty regarding the accuracy of these predictions. We can never be sure about how accurate our predictions are. And so that's why there is this spectrum of projections. But the average of all of our models over time give this relatively straightforward line. And what we see is that, and actually it matches, we're at almost 1 degree Celsius of warming currently. And you see that it just is projected to keep on going up and up and up. So if we use the average of the models, we can get a more accurate overall picture. All right, it is time to climb. Let's go underwater. All right, I want to see at least 12 people on this time to climb. If you're just on the chat, but you've tuned out, tune back in. There are 11 people on the Nearpod. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's go, let's go.
Here's what's up, dog.
Not much. How about you?
Ah,
That was a good one.
That's not me though, so.
oh.
Yeah.
All right.
Sorry, I know.
I'm gonna get started.
Set yours truly.
truly.
Oh God. Chill.
What's up, dog?
Doing stuff. I'm serious.
There's a vicious dog attack happening.
Yeah.
All right, Mr. Town, I'm glad you got that one right.
Yay.
All right, Alanis, jumping into the lead. Last question, make it good. Great job, Alanis. Great job, everybody.
No.
Have a great weekend and check in.
Mr. Dutton,
Yes, Mr. Tao.
real quick, what's the plan for next week again?
So, just needed to get off that music. All right. The plan for next week is Monday, Wednesday, and Friday from 9 to noon. I will be on to answer questions, to go through some meditation, some exercises, and also work on some goal setting and some long-term planning.
Awesome. Looking forward to it. Thank you all for
All right.
being here.
Same.
Have a wonderful weekend, guys. Feel free to email, stay in contact. We're always available.
Stay safe, everyone.